Section 13.1, we are looking at solutions. So our whole chapter now is looking at solution and solution chemistry. So we should start by defining what a solution is. We talked about solutions slightly way at the beginning of our whole adventure into chemistry. When we were talking about mixtures, we said solutions were certain types of mixtures. Typically liquids, typically salts dissolved in water would be a solution. Now we actually are going to have a much broader definition of what a solution is. However, it is still considered a mixture. Mixture means it has no set ratio of pieces. These aren't compounds. Nothing is bonded together. This is stuff typically dissolved in another type of stuff. And what we mean when we say dissolved, we say something is soluble in a certain liquid. So one thing dissolves in another. That is soluble in the liquid because it dissolves. So remember, when we look at solutions, often our solutions, when we think about solutions typically we're going to think about them as homogeneous solutions. So this is a volumetric flask with some water, put some salt in it. The salt disappears. Well, it doesn't disappear, it dissolves in the water, correct? Well, that makes it a solution because there's two different compounds in there. There's the sodium chloride, there's the water. Now, again, they're not in any set ratio, so it is a homogeneous solution. We can also have solutions that are maybe not always so homogeneous. We might think of milk being really homogeneous, but really it's a heterogeneous mixture. As you can see, the particles, it's not so uniform. So whether something is homo or heterogeneous, it's a little bit difficult to grasp right away. Typically, homogeneous are going to be completely uniform. If there's non-uniformity at all, we're going to say it's heterogeneous from now on. So very important to get the definition down. A solution is a homogeneous mixture of two or more substances. Here's an important part to it. In a single phase. So solutions, often we talk about solutions being liquids. Probably 90+% of the time, they do not have to be liquids, though. We can have gaseous solutions. We can also have solid solutions that go by our definition in some periods of time. So notice in this one, we have a solution where we have one liquid in another liquid. This is still a solution. We have ethanol that's being poured into water. Ethanol and water, that's a solution. Again, it's a mixture of two different things where they mix, they dissolve in each other. So let's look at the components of these solutions. If we can look at the same page here, I'll erase this stuff. Now, we have two terms to define what makes up our solution. We have what's called the solute and what's called the solvent. Now, typically the solute is what dissolves in the solvent. So if we go back to the first page, and this one is really easy. Our solute is sodium chloride. We take our solute, we put it in the water. Water is what we call the solvent in this situation. So the solute is what's dissolved in the solvent. However, our definition isn't quite so easy like that. Solute, because if we look again, sorry, I'm a little bit rambly. If we look again at our ethanol water mixture, well, who's to say what is dissolving what? Is it the ethanol dissolving in the water or the water dissolving in the ethanol? So in this type of scenario, what we say is whatever there's less of, so if there's less ethanol, then we call that the solute. And if there's more water, we're going to say it's the solvent. And again, this is one of those situations where the vast majority of the time, water is going to be our solvent. It does not always have to be our solvent. Our solvent is defined by whatever there's more of, essentially. So if you read in your book here, the detail in your book, it says if you have a 50-50 solution of ethanol and water, you can't really say what's the solvent and what's the solute because they're in equal proportions. Now again, typically the solute is going to be something like a salt, something that's going to dissolve in our water. That's going to be what exists the vast majority of the time. Now again, a little bit more stuff we should talk about these homogeneous solutions. These solutions, the dissolved solute particles, so those sodium chloride, if we think of them, or the ethanol in the water, they're so small they can't be seen, and they are mixed in the solvent indefinitely, so they don't separate. That's an important idea, because as we go on, we're going to look at some solutions that separate. Our solutions that we're talking about now, they do not separate. They would stay together indefinitely. And notice what it says here. If we put them through filter paper, if we pour that ethanol water mixture through filter paper, it can't separate the ethanol. Same thing if we pour salt water through filter paper, it can't separate the salt that way. So these are very small particles that are dissolved in the solvents. Now notice we said there was other things that could be solutions that we could say have solutes and have solvents. So notice we can have a gas dissolved in a gas, or a gas mixed in a gas. Really, maybe dissolved isn't the right word in this context, but we can have a mixture of gases, and that mixture of gases can be a solution, or is described as a solution. So the smaller gas, in this case oxygen, is in some nitrogen. There's more nitrogen, so nitrogen would be our solvent. So this would be like air. Air is, the vast majority of it is nitrogen with some oxygen and other things. So it'd be oxygen would be the solute in air, and nitrogen would be the solvent because there's more of it. Now you can also have a gas dissolved in liquid, like your soda pop. So there, in your soda pop, there's carbon dioxide in water. The carbon dioxide is a gas. There's less of it, so it would be considered the solute because it is dissolved again in the larger amount, the water, which is the solvent. You can have a liquid in a gas, like water in the air. This one's a little bit goofy to think about, but we can have water vapor going up into the air. It's liquid water in the air. It can be a solution. Think of, if you're thinking about this one, it doesn't really make sense, think of like a fog would be a solution. We'd have water vapor that is in the air. We could also have a liquid dissolved in another liquid, like we said, the alcohol in the water, a liquid in a solid, which is kind of a goofy one we don't see very often, but the scenario they have here is mercury in silver or in tin. So it's basically an alloy where you're using mercury as the liquid going in, a solid in a liquid, which is probably our most common type of solution that we think about, like sugar and water, or salts in water. Or we could have, this is the weird one that people always forget when we think about solutions, we could have an alloy, a metal alloy. One solid, essentially as a solute in another solid, could be defined as a solution. So here's an example of that. Gold, this is pure gold as elemental gold. Again, elemental gold, as we've talked about before, isn't really good for much because it is so malleable. You can't really use it for jewelry. Has some great properties, though. Is unreactive, great conductor of heat and electricity. But typically when we use gold for anything, it is used as an alloy. We mix in another metal to make it a little bit stronger, more durable. That alloy can be considered a solution where the silver, the smaller bits that are mixed in, could be, well, let's look. 14 karat gold, it says, is 58.3% gold. So that means the gold is the solvent, the silver is the solute in this instance. So now we want to look at other types of solutions, and really we can't define them as solutions because the particles don't stay into the solvent. There's solute and there's solvent, but they don't stay together, and that would be a suspension. So a good idea of a suspension, or let's read what, again, your book says about suspensions here. If the particles are so big that they don't stay in solution, so what we said about solutions is that the particles were so small, they would stay in the solvent indefinitely, and we could not filter them out. Well, that is not true with a suspension. In a suspension, our particles are larger, so they can be separated. This is called a suspension. So what we want to think about is like muddy water. So if I take a jar of muddy water, I mix it up, it's going to look like this. We see the particles moving all over. But if we let it sit on the counter for a while, that sand, the mud, will settle out on the bottom. That would be a suspension. So like it says in your book, they can stay in the solvent. Those solute particles can stay in the solvent, but only if they're constantly stirred or agitated. And sometimes I feel constantly agitated, but that would be a different use of the term. Now, colloids are kind of another spot along the continuum here. So we had solutions where you have very small particles that they stay in the liquid indefinitely. We have suspensions where they'll filter out over time. And we have colloids. So colloids, like it says, have particles that are intermediate in size between the solutions and the suspensions. So they have large particles, large particles that don't really dissolve per se, but they stay in the liquid. So they kind of stay cloudy. So one example of a colloid is milk. So milk is water. It is essentially fat, butter fat that's suspended. Well, I shouldn't use the word suspended because that would be something else. This is a colloid. So we have little particles of fat that are in the solvent of water, and that's what our milk is going to be. So how do we tell the difference? Because they seem kind of similar. Here's some examples of colloids, by the way. You can just go through them. A gel is a type of colloid, so you have a solid network extending throughout the liquid, like gelatin. So we can think of Jell-O as being a classic colloid, where you have particles that are suspended. They're not going to come out. Foams are colloids. A lot of aerosols are colloids, where we have things dispersed throughout. So again, hold on, we'll go back to that, but I want to look at this table. This kind of sets it out a little bit easier. So here's what we're comparing: our solutions, our colloids, and our suspensions. Our solutions, again, are homogeneous, very small particles that do not separate on standing or by filtering and do not scatter light. That is a solution, okay? Very homogeneous. Now, a colloid is heterogeneous. And again, like milk, it can look like maybe it's homogeneous. It's a little bit hard to tell by looks all the time with colloids. But they have larger particles that do not separate on standing, and they cannot be separated by filtration. But here's maybe the big difference. They will scatter light. So if we look down here, this is called the Tyndall effect, is that if we shine a beam of light through a colloid, it will scatter that light, and it will look murky, I guess. And seeing that the light is scattered, it doesn't pass straight through like it would perhaps a glass of water or a glass of salt water, any type of solution. Now, if we go to suspensions, again, our particles get a little bit bigger. And notice they do have particle size. So these are less than 1 nanometer, between 1 nanometer and 1,000 nanometers, which actually is a very broad range, or over 1,000 nanometers. Now, suspensions, the particles are literally suspended in the solvent. I'm going to use the word solution. Solvent is probably the better word for that. But the particles will be settled out, and they can be separated by filtration, and they can scatter light, but they're not transparent. We can't see through them. So that is really the table we want to focus on when we want to think about the differences between these words. And again, it's a lot of vocabulary, so you want to spend some time with a table like this. Look at some examples of each so they make sense in your mind here. So the last thing in this unit is we're looking at the solutes that are dissolved in the solvents and whether or not they're electrolytes. Well, what an electrolyte will do is electrolyte will conduct electricity. That is what an electrolyte is. Well, what do you need to conduct electricity? We need to have free charges. So we've talked again about this a little bit before. All of our ionic compounds that dissolve in water are electrolytes because, for example, sodium chloride, which is our constant example, when it dissolves, it produces sodium and chlorine ions in solution. So it has a medium for the electricity to flow through. If we have an electrolyte, there has to be charges in the solution for the electricity to flow through. So here it is, sodium chloride. If we set up our little apparatus here, try to run electricity through it, the light bulb will light up because there is a path for the electricity to follow because there's sodium ions, there's chlorine ions. There is ions in the solution. So ionic substances, hence the name ionic, produces ions in solution, and it is an electrolyte. Now, something like water dissolves, or something like sugar, dissolves in water. It will dissolve, but when it dissolves by the water orientating itself around the whole molecule, and so there's no free ions, and so it is a non-electrolyte. So a lot of our non-polar substances, a lot of our organic compounds can be non-electrolyte solutes. Other things, notice acids. Acids are going to be electrolyte solutions because when acids dissolve in water, they produce hydronium ions, or hydrogen ions, we can think of it as well, and perhaps some other type of ion. But acid solutions, salt solutions, as electrolytes, things like sugars are going to typically be non-electrolytes. Okay, so let's define these. And again, one time we might have defined all of these as homogeneous, but we're getting a little bit better in our definitions. So tap water, again, tap water is going to be a perfect solution where we can see through it. It doesn't scatter light, hopefully, unless you have some really dirty tap water. So B is going to be homogeneous. It's going to be a homogeneous solution. If you filter your tap water, hopefully you don't get anything out in the filter, so that would be a homogeneous solution. Orange juice actually is going to have some particles in it. So we could think of orange juice more as a colloid or even a suspension if we have some pulp that is in that solvent. So if you have to mix up your orange juice, you have to mix it up because this is suspension and you're trying to get those particles back up into the solution itself, into the solvent. What else do we have here? What substances are... So what are substances called whose water solutions conduct electricity? Those are electrolytes. Again, electrolytes have dissolved ions, so they can conduct electricity. Why does a saltwater solution conduct electricity? Well, because it has dissolved ions. A sugar solution does not conduct because it does not have dissolved ions. We could make a drawing of that, but it is on that previous chart. So let's move on to our other questions. Describe one way to prove that a mixture of sugar and water is a solution and that a mixture of sand and water is not a solution. Again, a solution will not be separated by a filter. If we have sand and water in perhaps the suspension, if we run that through a filter, we can separate the sand. So a solution cannot be separated by a filter. As one example, again, we could also do the Tyndall test. We could see if it scatters light. So if we have just sugar or salt in water, it's not going to scatter light. But if we have a suspension where we have some dirt or sand in water, it either is not going to be transparent, or if it is transparent, it will scatter light. So now, last one, what is the solute and solvent in each? Well, if we have 14 karat gold, again, what we said was the silver was the solute, the gold is the solvent because it's in the larger amount. Water, vapor, and air. If we have fog, the water is the solute, it's in the smaller amount, the air is the solvent. Carbonated or sparkling water, so if we have soda pop, CO2, gas, is our solute, water is our solvent, because that's what it's dissolved in, that's the larger amount. Hot tea, well, water is the solvent, and whatever your choice of tea is going to be your solute. Thank you.